Hello again. Please turn to page 13 of your notes if you haven't already, and we'll go ahead and get started. So today what we're going to talk about is shear stress and how it relates to viscosity and strain rate. Okay, and here's our equation. Shear stress equals viscosity times strain rate. Now this particular equation is a simplified equation. It's really only good for velocity going in one direction, so hopefully you recognize that u is the x direction of velocity. Okay, and we're going to assume we just have velocity going in that x direction, but it's changing in the y direction, meaning at one y position you have one velocity going in the u direction and the x direction, but at a different y position you're going to have a different velocity, so it's changing in the y direction. Okay, so that's our equation, and what we're going to do is talk about all three parts of this: the shear stress, the viscosity, and the strain rate. And right now what we're going to do is start with the shear stress. So shear stress is a lot like fluid friction. And it's a force per unit area, just like normal stress is. Normal stress in fluids is pressure, and that's going to point straight at your surface. Shear stress, on the other hand, is going to act parallel to your surface. It's going to have units just like pressure of, say, newtons per meter squared, which is a Pascal, or pound force per foot squared, or even PSI, which is pound force per inch squared. Okay, so it's a force per unit area just like a pressure is. But unlike pressure, it acts parallel to a surface. So you might want to think of, say, a water ski. The water pulls back on the ski pulls the opposite direction on the water. Okay, so most of the time, just like with the ski, we're not so interested on the water pulling on itself. It does. If the velocity is changing, one molecule that's going a different velocity from the next will pull on that other molecule. What we're usually interested in, though, is what's happening at a solid surface, and we're going to call that solid surface a wall. Okay, so we're going to abbreviate our wall shear stress. We're going to call it tau sub W for wall, and that just means at any solid surface. Okay, and our wall shear stress, it's still going to be mu du dy. Okay, but what we're going to normally do is draw our coordinate system so y equals 0 at that wall. And so then we can say wall shear stress is mu du dy at y equals 0. So basically calculate this equation, mu times du dy, and once you're done with that you plug in y equals 0 and you got your wall shear stress. Okay, so that's how you find the wall shear stress, but again, that's not exactly what we're usually looking for. What we're usually looking for could be the total forces on that wall, on that solid. Okay, so since stress is a force per unit area, if you want to get back to that force, you're going to just multiply by area. Now that only works, of course, if the shear stress is constant over that surface. Okay, so remember it's acting parallel to a surface, so if you have a constant shear stress acting all over some surface, all you have to do to get the total force from that shear stress is say it's equal to tau at the wall times that area. That's as long as tau is constant over that whole surface. Okay, so we'll do that a lot. Sometimes we're going to also have spinning objects. So let's say we have a cylinder that's coming out of this page, and maybe it has a radius of r, and it's spinning. Okay, so since it's spinning, the wall is spinning, there's going to be a shear stress right next to the wall. It's going to act, the fluid's going to act opposite of the direction of the flow here, or the moving surface. Alright, so this is moving that way, this is going to go the opposite direction on the wall. So the net forces on every side, you're going to have one shear stress going in one direction and an opposite one on the other. So the net forces are going to come out to be 0. but the net moment is not. So we're going to worry about moments in this case. So if you remember, the total moment is going to be your force times your radius, your perpendicular distance to that force. And it's going to act all over this whole surface, so we can just say, well, that force, if it's constant, it's going to be your tau at the wall times your A, and now to get that moment, we're going to multiply it by R again. All right, so that's what I got for shear stress. Go ahead and stop and do quiz questions 1 and 2, and then we'll start the next video.